Starting notes on 8.3. So we are looking at
one sample z intervals for a population mean as well as a t distribution and working through that as well. So one big thing about 8.3. In 8.3 we are always looking for mu. Every time. Always looking for mu. Okay? So a one sample z interval for a population mean, the formula is x bar plus or minus c star times standard deviation over the square root of n, which if you come to realize what that is, that's the exact same formula as what we talked about before, your statistic plus or minus your critical value times your standard error, okay, or critical value times that is margin of error. So it's all the same formulas. It just depends on whether you're using population mean or if you're using a sample mean or a sample proportion. Now the problem with this is it's very rare. So rarely do we know standard deviation if don't have our mean. Okay? So very rarely are we actually going to be able to do that. All right? And then we're going to list the conditions below. So we'll come back to what conditions have to be met in order to do a one sample z interval for a population mean. Now, like I said, it's very rare that you have all the conditions you need for a z interval for a population mean. So in those cases, we're going to use what's referred to as a t distribution. T distribution. So when we're doing a t distribution, we're drawing a simple random sample from a population that has a normal distribution that is normal with a mean and standard deviation. But again, we don't know what those are. We don't know mean, we don't know standard deviation. We just know that it is normal. That's the important part. Okay? The statistic t equals x bar minus mean over sample standard deviation over the square root of n. Now, if you notice, that is the same thing as the z-score formula in finding a z-score, but instead of using x and rho, we're now using our sample mean and our sample standard deviation. Okay? And it has a t distribution with degree of freedom, that's what df stands for, is degree of freedom, equaling n minus 1. Okay? Now, you don't need to know what degree of freedom is outside of knowing that instead of using sample size instead of using n for t distributions, we use degree of freedom, which is always just one less than your sample size. Okay? If your population distribution is not normal, okay? If it's not normal, your t statistic will have a t distribution when our sample is large enough. Now, so again, since we're working with means, remember our normalcy definition for means is 30, and you're going to find it's fairly similar when it comes to t distribution. So degree of freedom, again, you don't really need to know what degree of freedom is outside of the fact that it's n minus 1. Pretty simple there. Standard error of our mean. So standard error of x bar is just rho divided by the square root of n. I'm sorry, not rho. Sample standard deviation divided by the square root of n, because we don't know rho. So S of x equals our sample standard deviation. Okay? And it describes how far x bar will typically be from mu. Okay? Alright, so last vocab term we have to talk about is a one sample t interval for a population mean. Like I said, most of the time you don't know mean and standard deviation, so you're not going to be able to do z interval. So in that case, we're going to do a t interval. So when we're doing a t interval, we don't know the standard deviations. That's the key value. If you don't know standard deviation, you have to use a t interval. So when conditions are met, and again, we'll get the conditions in a second, a C% confidence interval for the unknown mean mu is x bar plus and minus our t statistic times s of x over the square root of n. Okay? Where t is our critical value for a t n minus 1 distribution with C% confidence of data between negative t star and t star. So in that case, we're talking about if we have a 95% confidence, that means there's so much data between your negative t value and your positive. So it's very similar to what we did with our z score table, table A. We're now going to be working with a different table using our t distribution, which is usually table B. So you'll see it labeled t distribution on top. We'll talk more about it as we go. But the big thing is you have to understand that we're using a different table. All right, steps for constructing confidence interval for mean. So there's 4 steps. Okay, very similar to what we did with the 4-step plan. So step 1, what parameters do you want to estimate? And at what confidence level? Okay. Step 2, identify the proper inference method and check conditions. And again, usually, for right now, it's usually a one sample t interval for mu. So the big thing we have to get right now is if we're doing a proportion, we're doing a one sample z proportion for p, and if it's a mean, you're going to have to do a one sample t interval for mean. Okay, step 3. So if we're thinking in terms of 4-step plan, that was state, that was plan. Now we're to our do step, step 3. So if conditions are met, perform the calculations. Okay, if you get a problem like this on the AP test, they're not going to give you one of these that does not work. Okay, that would be a waste of a free response question. So if you get one of these, you have to understand that the conditions are going to be met. And then step 4, that's the state plan do, conclude. Interpret interval in context. And it's very important. Again, we're going to be working with blurbs that you understand what that is. All right. So, conditions for calculating a confidence interval for mean. Okay, random. So you have to have data from a simple random sample of size n, or you have to be told it's a random experiment. Okay. 2, your population is normal. If that's the case, then you know it's automatically normal for your sample, or n has to be greater than 30, which again means it's approximately normal. So we can assume it's normal at that point in time. Okay? And 3, each item is independent of next. And 2, our 10% condition. Okay, if you're told it's an experiment, you don't have to do a 10% condition. If you're doing an experiment, you're told it's an experiment, you just automatically assume it's independent. Our 2 stars here. Must have all 3. Every time. Must check all of them. Okay? The second one there is also really important. If one of these is failed on the AP exam, which they'll sometimes do, say that one of these is failed, do not construct the confidence interval. If you construct the confidence interval after saying it's false, it will be wrong. So you have to understand that as well. Alright, so there's the bulk of the vocab / application stuff. So now what we need to do is actually do some math. Alright, so constructing a confidence interval for mu. There's 3 ways to do it. So again, it's estimate plus or minus the margin of error. That's the very first way we learned how to write. That's the way it's going to be on the AP test. You're going to have to, on the formula sheet, you're going to have to know these from memory. Alright, second way we talked about it is statistic plus minus critical value times standard deviation of a statistic. The third way, and this is the one you really need to know, it all depends on whether or not you're given standard deviation. If you're given standard deviation, it's easy. It's x bar plus or minus z star times rho over the square root of n. Okay? If we don't know it, assuming we don't know it, then it's x bar plus or minus t star times s of x over the square root. Okay? Alright, so, and then if they ask you again for margin of error, it's going to be greater than or equal to z star times square root of n, or margin of error is greater than or equal to t star times s of x over square root of n. Okay? Alright, now we're into examples. So it says you want to estimate the fuel efficiency of Ford Focus automobiles with 99% confidence and a margin of error of no more than 1 mile per gallon. Preliminary data suggests that standard deviation is 2.4 miles per gallon is a reasonable estimate of the standard deviation for all cars of this model and make. How large of a sample do you need? All right, so margin of error in this case, 1 mile per gallon. So we're going to go 1. It's greater than or equal to. We're told it's a 99% confidence interval. Well, at 99% confidence, we use 2.5758, and that comes from the chart that we talked about the other day. Standard deviation is 2.4 over square root of n. That's what we're trying to solve for. So again, we're trying to isolate n in this case. So we're going to divide everything by 2.5758, both sides. Okay? If I do that, I get 0.3882 is less than or equal to 2.4 over n, the square root of n. So now we cross multiply. Put that over 1, cross multiply, I get 0.3882 times square root of n is greater than or equal to 2.4. Divide by 0.3882. So I get the square root of n is greater than or equal to 6.18192. Square both sides, n is greater than or equal to 38.21. Okay, so that means we need a sample of at least 39 cars. If we have 39 cars, then we can assume that standard deviation with less than, or at most, 1 mile per gallon error. Okay? All right, so that's our first example. Using this. All right, so next. We're going to talk a little more about a t-distribution. Okay, this chart is on page 512 in your book. Big thing here is, if you look, the darker purple, the more, so basically what I'm trying to tell you here is the smaller the sample with the t-distribution, the more areas within the tails. And that's bad. We don't want area within the tails. So the larger the sample, as you see here, when k is infinity, when k is infinite, it's exactly a normal curve. Okay? When k is infinite. So a couple facts about a density curve, or t-distribution density curves. Okay? T-distribution, similar in shape to our z-distribution. And another name for our z-distribution is a normal curve. Okay? And like we talked about initially, the spread of t is greater than the spread of z. And again, when I'm referring to z, I'm referring to a normal curve. Okay? Which means that t has more data in the tails, which you don't want if we're assuming normalcy. Okay? As our degree of freedom increases, so that means the sample size is going up, our t distribution approaches normal. Okay? And that's due to our sample getting larger. So just like before, if our sample is greater than 30, then you're in good shape. All right. Now to actually use a t-distribution a little bit. Find the critical t-value for each of the following confidence intervals. 95% confidence interval with n equaling 8, or 7 degrees of freedom. So there are two ways to do this. Okay? So right away you know that degree of freedom is n minus 1. So that's 8 minus 1, or 7, which is why we have 7df in the parentheses. So you have two ways you can do this. The first way is to look at table B in the back of your book or in that formula sheet packet that I gave you. And you match up 95% confidence interval with 7 degrees of freedom. You come together on table B, you get that T star is 2.365. Okay? That's the first way to do it, is using table B. The second way to do it is using a calculator. Just like we talked about, how do I find Z star? I can do inverse norm with tail area. you can do the same thing now for inverse t. So you do inverse t. So if we have a 95% confidence interval, you do 1 minus 0.95 divided by 2. So that's 0.05 divided by 2, which means each tail is 0.025. So I take 0.025, which again is our tail area, my degree of freedom, which is 7, and that gives me 2.365. So the calculation on your calculator, if you want to do this, is inverse t of your tail area, comma, degree of freedom. That's how you do that on your calculator. All right? Same thing for the second one here. 80% confidence. So if I do table B, find 80% confidence with a size 19 degree of freedom, I get 1.328. Again, lower confidence level, so it's going to have a lower t star. And on a calculator, inverse t, tail area is going to be 10%, because I have 1 minus 0.8 over 2, that's 0.2 over 2, which is 0.1. And degree of freedom is 19, and I get the exact same answer, 1.328. All right. Normal C condition for T. Normal C condition for T. You still need random, and you still need 10%. All right. Now, there are a couple. You can actually do this with less, but if it's less than 30, so we're looking at 3 different ways. If n is less than 15, if 15. Okay, so there's 3 different conditions. If our sample is less than size 30, so it's less than 15 in this case, you must graph it. And use T procedures. If there's 2 conditions. 1, it's close to normal. What do I mean by that? For something to be close to normal, it has to be symmetric and it has to be single peaked. And 2, no outliers. So if it's less than 15, you must graph the data, see that it's single peaked, symmetric, and has no outliers. If that's the case, you can do the t distribution as long as it's random and meets the 10% condition. All right, if it's between 15 and 30, we can use T procedures. We don't have to graph it this time, unless we have outliers or strong skew. Now, some of you may be wondering, well, can we tell skew without graphing? To be honest, no, you can't. So if you can't look at a data set and, yeah. So basically, you're going to at least want to sketch it for 2. 1, you absolutely have to graph. Actually, let me renege. You have to graph 1 and 2. It's less than 30, you have to graph it. And then 3, use your T procedures no matter what. Okay? And these are similar to large counts condition for a normal curve. So that process is very similar to what we had to do for normal curves. All right. Again, at any point in this, if you need to pause, go back, you can. I'm going to strongly suggest, hopefully, at least watching this once, but you may need to watch it more than once. Okay? All right, example 3. 130,000 high school students took the AP Stats test in 2010. Pre-response section of the exam consists of 5 open-ended questions and an investigative task. Each pre-response is scored on a 0 to 4, 4 being the best. For one of the problems, a random sample of 30 students' papers yielded the scores that are graphed below. Okay, so the mean for this score is 1.267, and the standard deviation is 1.230. Part A, find and interpret the standard error of the mean. So if we look at this data set does have a strong skew. But in this case, it doesn't matter because our sample is of size 30. Since we're of size 30, we can do it, and it does not matter. So we have our mean. We have our standard deviation. So standard error of x bar is just going to be standard deviation over the square root of n, which in this case n is 30. Standard deviation is 1.230. Divide that by the square root of 30, which is 0.2246. Then asked us to interpret it, so we have a blurb for standard deviation. It's if we take many samples in the same manner of size 30, our sample mean will typically be within 0.2246 points of mu for given questions. Okay, so that's part A. So if we take many samples in the same manner of size 30, our sample mean will typically be within 0.2246 points of our population mean, which is mu, for a given question. Okay? All right. So part B. Part B. Again, confidence interval. Every time you do a confidence interval, you have to do all 4 steps. So, state. What are we trying to find? We're trying to find a 99% confidence interval okay? 99% confidence interval for the mean scores of 30 students on AP Stats test. The 3 responses. Plan. So, we're not given mean. We're not given mean in this case. Okay? And we're not given our absolute standard deviation. We're given our sample mean, sample standard deviation. So we have to do we will construct a 1 sample t interval for mean. And why? Because we don't know our population mean or our population standard deviation. Okay? Do. So we have to check our conditions. Check our conditions. Well, n is greater than 30, so we know it's normal. We're told in the problem, we're told it's random, so that's good. And then independent, 30 is less than 10% of all people tested. So we're good there as well. So we know it fits our t distribution. So we're going to do our t sample. So our 1 sample t. First thing we got to do is find, so we want a 99% confidence interval, which means each tail is 0.005. We have a degree of freedom of 29. That's 30 minus 1. So that means T star in this problem is 2.756. So if we plug into the formula, x bar plus or minus T star times the standard error, we're going to get x bar, we said was 1.267 plus or minus 2.756 times our standard error, we just found in part A, was 0.2246, which means our scores fall in the range of 0.6480 to 1.8860. So that's saying, on average, our scores should fall between 0.65 points and 1.9 points. Okay? And then on the AP test, you should do the conclusion. For the sake of time, we're not going to. Well, okay. So if we wanted to write out our conclude, it would look like this. I am going to do it, I guess. We are 99% confident that the interval from 0.648 to 1.886 captures the true mean for AP Stats free responses in 2010. All right? So there's your 4-step plan for that problem.
This is one problem.
All right, so to wrap this up, okay, to wrap up these notes, so I'm going to teach you a little trick here called ZAPTAX. Okay, so we're going to use a Z distribution for proportions and a T distribution if I'm given sample means. We can only use a Z distribution if we know the standard deviation for x bar. Okay? And again, remember ZAPTAX. So if we have a Z distribution, use Z and P go together, T and x bar go together. So what this stands for is if you have a P hat or a P, if you're working with proportions, use a Z distribution. If you have an x bar, you're using a T distribution. Okay? Finding a T star. How do I do that on the calculator? Second, bars. It's under distributions. It's number 4. Inverse T. And again, what do I need for that? Tail area and degree of freedom. How do I find degree of freedom? It's n minus 1. Always write that down, even if you use a calculator. How do I do a one sample T interval on a calculator? You're going to go to Stat, Test, and you're going to push 8 for T interval. Okay? Then, under that, it's going to ask you for some statistics. What is your x bar? What is your sample standard deviation? Not your standard error. What is n? What's your confidence level? The star here. If you're using a calculator on the test, on the AP test, say you use the calculator, don't show the formulas as well. Say did a one sample T interval for mean on the calculator. Okay? So that is 8.3. That is all the notes. That is everything you're going to need to know. I'm going to pull up one other thing so you can see what the homework is for 8.3 and the review. Alright, so let's go ahead and get rid of this. So 483, homework, page 505 through, or I'm sorry, page 527 to 530. It's 55 through 55, 57, 59, 61, 65, 69, 71, 73, 75, 78. Then for the review, you also need to do the Frappy on page 530, and then problems 1 through 10 on pages 532 and 533. So this, you should watch this Wednesday while I'm gone. Thursday, you will have time to work on the review. Friday, you will have time to work on the review. Monday, you will start the test. So it is important that you have these things in place. Okay? The plan is for you to start the test on Monday. If you have questions, please email me, let me know. All right, hopefully this helped.